Have you ever just stopped and wondered how a brand new idea actually clicks inside your head? Well, today we're going to unpack the science behind that very moment. All right, let's get into it. I mean, really think about it. How does a little kid go from pointing at every furry, four-legged animal and shouting, "Doggy," to actually knowing the difference between a dog, a cat, and a squirrel? That little spark of understanding, it's one of the most basic but also amazing things our brains do. And that's exactly what we're exploring. So it turns out this everyday miracle of just figuring stuff out, it actually has a name in science. It's called concept learning. And it's the bedrock process that lets us build our understanding of, well, pretty much everything. Yup, that's right. There's a whole field of study dedicated to just this. You've got cognitive scientists and mathematical psychologists whose entire job is to try and map out exactly how we build up our mental library of ideas, from something as simple as the color red to something as incredibly complex as justice. So, how does it all work? Well, when you boil it all down, the process is actually surprisingly simple. At our core, we're all just making educated guesses, over and over and over again, and just seeing what sticks. And of course, science has a name for this process: hypothesis testing. You can think of it as the engine that drives all concept learning. You form a little theory, you test it out on the world, and then you adjust it based on what happens. It's what you're doing when you try a new key on a stubborn lock, and it's exactly what a scientist is doing in a multi-million-dollar lab. And this loop just illustrates it perfectly. Let's go back to our kid, right? Step 1, they make a guess. Anything with 4 legs and fur is a dog. Step 2, they see a cat walk by. Step 3, they test it out, shouting, "Doggy!" Step 4, they get corrected. "No, sweetie, that's a kitty." So they change their guess. Okay, new rule. It's got 4 legs, fur, and it has to bark. This loop is running constantly, all the time, just sharpening our understanding of the world. But, scientists didn't just wake up one day with this neat 4-step loop. Our understanding of this stuff was built over decades. So let's take a quick look back at the first models, the original blueprint for how we thought learning worked. The very first people to tackle this question saw it almost like a logic problem. They thought learning a new concept was all about finding that one single correct rule that defined it. And they used a ton of math to try and model how we might find that perfect rule. Now, what's so interesting here is you can see them building the idea brick by brick. They looked at how the order of information we get changes how we learn. They studied how we learn to tell two similar things apart. And they looked at how getting a, "Yep, that's a dog," versus a, "Nope, that's a cat," really shapes our learning process. All of this was absolutely critical groundwork. And this quote just captures the whole vibe of that early research perfectly. The goal was to find the one defining rule. Learning was seen as a binary thing. Your guess was either right or it was wrong. Full stop. It was a very clean, very mathematical way of looking at things, but maybe not a very human one. Which, of course, leads to the big question. Is that really how our messy, complicated, amazing brains actually work? Are we really just looking for one perfect answer, or is there something a bit more flexible, a bit more dynamic going on? And this is where our modern understanding takes this really fascinating turn. Researchers started to see learning not as this hunt for a single right answer, but as a constant, fluid process of updating our beliefs about what's probably true. Okay, Bayesian framework sounds super technical, I know, but the core idea behind it is actually beautiful and pretty intuitive. It suggests that learning is about stochastically updating our ideas, which is just a fancy way of saying we're dealing with probabilities, not certainties. Think of it like a detective. A good detective doesn't just have one suspect. They have a whole list, and each suspect has a certain probability of being the culprit. With every new clue, they don't just cross people off the list. They adjust the probabilities. That's what this model says our brain is doing. We're juggling lots of possibilities at once and constantly updating how likely each one is. So this slide really gets to the heart of this huge shift in thinking. We moved from a very black and white view of learning, you're either right or you're wrong, to a view that's full of grays. Learning isn't a sudden flip of a switch, it's a gradual process. Our beliefs get stronger and more refined with every new piece of evidence we see. It's less like a light switch and a whole lot more like a dimmer. And this new model helps us understand so much more about how we think. It explains how we learn even when we're not sure about things. That's the stochastic part, the probabilities. It shows how we can build big, complex ideas out of smaller, simpler ones. And it even helps explain why we aren't perfect learning machines, our bounded rationality.
This framework helps model our very human limits. But, of course, the story doesn't end there. Like any great scientific leap, this modern framework didn't just give us answers. It opened up a whole new world of fascinating questions for researchers to explore. Because that's the beautiful thing about science, right? Every great answer just leads to even better, more interesting questions. And now that we have this more powerful way of thinking about learning, researchers are pushing the boundaries even further. So, one of the biggest questions on the table right now is this whole hypothesis testing thing the only game in town? Or could it be that our brains actually use different strategies for different situations? For example, some researchers are exploring if maybe we learn by just storing every single example we ever see. That's the exemplar model. Or maybe our brain creates a kind of mental average or a prototype of a concept. And maybe, just maybe, in some simple cases, we really do just fall back on simple, hard and fast rules. The truth? It's probably a mix of all three. And here is another really deep question. Why is it so much easier to learn the concept of a chair than it is to learn, say, the concept of democracy? What is it about the very structure of an idea that makes it either simple or incredibly difficult for our brains to wrap themselves around? Well, to answer that, scientists use tools like Boolean complexity. It's basically a way to measure how complicated the underlying logic of an idea is. For example, a concept like it's red or it's round is logically way simpler than it's red and it's round, but it's not small. And what they're finding is that this logical complexity is directly tied to how hard it is for us to learn. So if there's one big thing to take away from all this, it's that our scientific understanding of learning has itself been a learning process. We started with this simple binary model of just finding one correct rule, and we've evolved to a much richer, more nuanced view of our brains as these incredible probability updating machines that are totally comfortable living in the gray areas. And that, of course, brings it all right back to you. Every single time you figure something new out, your brain is running this incredible program. So the only real question left is, what amazing new idea is your brain going to test out and refine today?